The best way to write parallel application is not to have to think about parallelism. We will solve the same problem as in the previous video, this time using a more higher level construct. The idea is that we will write a simpler algorithm in which we will split the problem in much more tasks. As BCL, we run each task as soon as a thread is available. Bordeaux threads offers low-level primitives to implement thread parallelism. Using Bordeaux threads, you can implement any parallel algorithm. The main issue is that it's really difficult to get it right. Using lock can easily lead to problems like deadlock. Moreover, in the solution we proposed last time, the number of threads was hard-coded in the algorithm itself. This was because it depends on the machine we run it on. If we use a little number of threads, we are not using all the resources available, while if the number of threads is too big, we spend more time switching tasks than solving the problem. Lparallel is a library based on Bordeaux thread that provides, first of all, a thread pool. At the beginning, we define how many threads we want to start. The number depends on the machine and on the problem at hand. If the problem uses a lot of CPU, the number of tasks should be the same as the number of CPUs. If the problem uses a lot of I/O, the number of tasks can be larger than the number of CPUs. Then we have just to submit a task, and as soon as a thread in the pool is available, it will be executed. Moreover, Lparallel offers higher level constructs. There are constructs that let us write an algorithm thinking less about starting and joining threads. There are many of them. We will use futures. Let's talk about what are futures. When we call a function, we have to wait for it to finish. We can say that this is a blocking operation. A future is a wrapper around the result of an expression. As soon as the future is declared, we get the control back and the program can go on. This operation is non-blocking. The result of the future is computed in a parallel task. We can go on, as soon as we really need the value inside the future, we have to force it. If the value is available, we get it and go on. While if the value is not available, we have to wait for it. This is a blocking operation. We are basically joining a thread. Let's make some example on the usage of a future. First of all, we have to load Lparallel. At the beginning, we have to create a thread pool. We can just assign the result of makeKernel to the global variable kernel. MakeKernel takes as parameter how many threads we want in the pool. In this case, they are 4. Then we can actually create the future. In this case, the future first of all sleeps for 1 second and then it returns the value 42. If we print the value of the future, we can see that it's not the result itself, but is an object of type future. To get the actual value, we have to call the function force. Now let's define again the future, but this time we sleep for 10 seconds. Let's declare the future again, this time sleeping for 10 seconds. And then we force it to get the value back. We can see that we had to wait for the sleep to finish. The first function, the call to future, returned immediately, but then force had to wait. Now let's see how we can apply what we have learned with future to sum the value of an array in parallel. We load Lparallel as usual. The first two functions, sum sequential and generate random array, are the same as in the previous video. I suggest you look at it first. Let's compile them. As usual, at the beginning we have to create the thread pool. We can see that we can run this form at the beginning and it's completely unrelated to the rest of the algorithm. And then we can see how to use futures to sum the reciprocal of the elements in an array. As usual, the function takes as input the vector and two indices from and to that defines the range in which we want to sum the reciprocals. Then we define two variables, total, which contains the number of value we are summing, from is included in the range while 2 is excluded, so the number of element is just the difference between 2 and from. And then mid contains the index at the middle between from and to. We need this because we will proceed using a divide and conquer approach. So if the range contains just one element, then the sum of it is just the reciprocal of that element. Otherwise, if we are in the else, we have at least two elements, and so we use a recursive approach. First of all, we call some future in the first half, and then we call some future in the second half. Those calls are not direct, but are inside a future. This means that they will be executed in parallel. Finally, we have just to force the result of those two futures. This algorithm works, but when the value of total is small, there is an explosion of recursive calls. For this reason, it's quite common to define a threshold, and then if the number of elements is less than that value, we just call some sequential. Now we can compare the performance of some future with some sec. To do this, we generate a really big array, and then we measure the time that we need to run some sequential and some future. We can see that the first one needed 0.3 seconds, while the other 0.1. The first one used just one CPU, while the other used 4 of them. We can run the same algorithm more times, and we can see that the result is quite consistent. Using futures, we could implement an algorithm which is quite simple, but can take advantage of multiple cores. For today, this is all. Let me know in the comment if you liked the video, leave a like and subscribe.